Hello and welcome back to the Science of Concrete Materials class. This is lecture number 32 and we will continue the discussion on the response of concrete to stress. Last lecture we discussed the modulus of elasticity and how it is determined. Let's now take a look at what is the modulus of elasticity of concrete is affected by. As you can see on this slide here, of course the concrete is made up of the cement, paste, matrix, the aggregate, and the interfacial zone. Okay, and of course the testing parameters affect this value as well. So the testing parameters of the concrete samples, for example, the moisture state of the specimen and the loading conditions. For the cement paste matrix, of course, the biggest effect will be like the porosity of the matrix itself, and that will affect the elastic modulus of the cement paste, which eventually also affect the modulus of elasticity of concrete. The aggregates, the volume of fraction of the aggregates, and the porosity of the aggregates. The porosity affects the modulus of elasticity of the aggregate itself, and that eventually will have an effect on the modulus of elasticity of concrete. Also the interfacial zone, and we saw in one of the models that predicts the modulus of elasticity of concrete does not rely on just the two-phase model, aggregate and paste, but also some models consider the interfacial transition zone. This one also, the properties of this zone will affect eventually the modulus of elasticity of concrete, of course, which is basically the porosity and the composition of the interfacial zone. And also, just as a side note, we saw how we can improve the properties of this zone, like the density, by reducing the porosity of the zone by, for example, using silica fumes, if you remember. Okay, so let's look at these factors in detail. Okay, as really demonstrated in this empirical equation number 1, if you remember, let me just go back to it here, these equations, this equation number 1, how this is basically the practical determinations or predictions of the modulus of elasticity of concrete according to ACI building code. And you see it depends on the unit weight of the concrete and the F prime C, which is the compressive strength of the concrete. Okay, so as we said, in this equation, the modulus of elasticity is related to the compressive strength and the density. So basically, factors that affect the strength should similarly influence the modulus. And this is, by and large true, so that you keep in mind. The dominant factor is, of course, the porosity, and the modulus will decrease markedly as the water-cement ratio is increased. So we have to remember that since the porosity changes that occur with the water-cement ratio are totally within the paste, okay? So this change in the stress-strain behavior of concrete is due to changes in the response of the paste that's related to the porosity or the water-cement ratio, as you can see here. Okay? So the modulus of elasticity of cement paste, denoted as E sub P, as you can see in this equation, has been found to be approximately proportional to the cube of the gel to space ratio. If you refer back to the hydration lectures for more on this subject. In terms of the capillary porosity, the relationship can be written as follows, as you see here in equation number 3, whereas the modulus elasticity of the paste equals to E sub G, which is, you know, the modulus elasticity of the hardened paste at zero porosity, times 1 minus the gel to space ratio, which is B sub C, okay, the capillary porosity expressed as a ratio, okay, of course to the power 3. All right, so, you know, a similar relationship also holds for the shear modulus, okay, as you can see in this figure right here. Okay, this is for the elastic modulus, this is for the shear modulus. Okay, for ordinary Portland cements, you know, the E sub G appears to be about 29 gigapascals, while the shear modulus G sub G is about 12 gigapascal. So one apparent inconsistency in the strength modulus relationship is the moisture dependency of the two properties. So the strength of saturated concrete is lower than that of the dry concrete, while for the modulus, the elastic modulus, the reverse is true. Let's keep that in mind, okay? The modulus of elasticity of concrete is much more sensitive to the amount and nature of the aggregate than it is, you know, to the moisture content, as you can see in this figure right here. Okay, so it is worth noting that the relative effects of the two conventional aggregates shown in the figure, basically gravel and limestone, should not be really construed as general, since the comparison applies only here, you know, to the particular aggregates used to develop the data for this particular graph here. You know, that is, in many limestones, you know, many limestones will provide stiffer concretes than those obtained with many types of gravel in some other cases. Okay, so this is not general rule, all right? The much lower elastic modulus of the porous lightweight aggregates, such as expanded clay or shale, has also strong influence on the elastic modulus of the concrete. That's something we have to keep in mind. So the elastic modulus of the lightweight concrete is about 40 to 80% that of the normal weight concrete, as you can see in this table right here. Okay, the stress-strain behavior of the lightweight concrete is nearly linear over, you know, a much wider stress range than it is for normal weight concrete. Equation 1, the one I showed earlier, applies also to lightweight concrete as well as normal weight concrete. However, you know, more accurate expressions are available for concretes with a strength higher, you know, than 40 MPa. So that equation, as I mentioned before, may not hold true for higher strength concrete. All right. Also, the stress-strain curve of the concrete and the modulus of elasticity is dependent on the conditions of testing. An important parameter is the applied strain rate, as you can see in this figure. As you know, we will see later in the next module probably, the higher the strain rate will be, the greater the strength and the higher modulus of elasticity of the concrete. But, you know, fortunately, in the time range normally required to test a specimen for our general purposes, which is about 2 to 10 minutes, the effect of the strain rate is very small. Okay, so the sensitivity of the modulus of elasticity of concrete to testing conditions is also demonstrated by the dynamic modulus of elasticity. You know, in the dynamic test, the concrete is subjected to very small strains, so its response is more closely related to the initial tangent modulus than to the chord modulus, as we mentioned earlier. So as a result, the dynamic modulus is about 20 to 30% higher than it is the static modulus, and of course dependent on the strength of the concrete. That's the dynamic modulus is used primarily to evaluate soundness of concrete and durability tests, as we will see when we talk about the non-destructive testing, for in situ evaluations. However, it may be more appropriate value when the concrete is to be used in structures that will be subjected to dynamic loadings, as the case is in the earthquake or impact loading. Also, the shear modulus, which basically governs behavior under shear stress, is not easily determined from direct stress strain measurements. It is probably best to determine by dynamic methods using resonant frequency or torsional vibration of concrete specimen. We will discuss those, I said, in the non-destructive testing next module. Okay, so these are basically the factors that impact the modulus of elasticity of concrete. We said the strain rate, the aggregate, the water cement ratio, which is basically the porosity of the cement paste. Okay, let's now move on to the next subject, which is the tensile strength. The tensile strength of concrete, as we know, is much lower than the compressive strength because basically of the ease with which cracks can propagate under tensile loads. The tensile strength of concrete is usually not considered in design. If you have already taken reinforced concrete design, you know that it is often assumed to be zero. However, it is an important property since cracking in concrete is most generally due to the tensile stresses that occur under load or due to environmental changes, such as shrinkage and thermal changes. So the failure of concrete in tension is governed by the microcracking associated in particular with the interfacial region between the cement paste and the aggregate particles, which we refer to as the interfacial transition zone. As we will discuss later, though, the tensile strength of concrete is most often evaluated using a flexure test, in which a plain concrete is loaded in bending, or using the split cylinder test, in which basically the cylinder specimen is placed on its side and loaded in diametral compression so as to induce transverse tension, as we will see later. In North America, there is no standard test procedure to measure the direct tensile strength of the concrete. A number of specimens, not yet really standard, none of them yet is a standard basically, are available to measure the fracture properties of the concrete under tension. So as tensile crack, basically what happened for the concrete under tension, as the tensile crack propagates, if you look at this, as the tensile cracks propagates through concrete, its leading edge often consists of multiple branching microcracks that eventually will coalesce into a single microcrack as the tensile displacement increases. As you can see here, that's really what happened. This is a schematic representation of how cracks develop and how we see them at the macro level. Okay, so here we see basically the tests I just talked about. This is the bending test, which is we measure the modulus of rupture from it. And this is the split cylinder test, and we measure the split cylinder tension strength. And this is a direct tension test, which is really it's not easy to perform, and there is no standard for this test adopted. Okay, so the values typically what we get is the modulus of rupture value is usually higher than the split cylinder value, and this is the lowest value, which is the value we'll get from the direct tension test if it is performed. So depending on the relative strength, tensile strength of the mortar, the aggregate and the interfacial zone, the macroscopic appearance of the surface, of the failure surface, may be smooth or rough. Okay, so a low ratio of aggregates to ITZ strength will result in a relatively smooth failure surface. As the relative strength of the aggregate increases, the failure surface becomes progressively more uneven, usually resulting in a higher tensile strength and improved fracture properties. So, okay, this is what happened due to the relative strength of the aggregate to the ITZ. Okay. Also, because the compressive strength is the principal material property that is measured for hardened concrete, the relationship between the tensile and the compressive strength is of particular interest to us always. In general, as the age and the strength increase, the ratio of the tensile to compressive strength decreases, as you can see on these figures here. Let me go back. Okay, so basically this is for various specimens, and the evaluation of the this graph here, right here, relating the modulus of rupture. If you go back, this is the modulus of rupture, and this is the split cylinder test. Okay, so this is relating the modulus of rupture to the compressive strength, and this is the split in tensile strength to the compressive strength. So as you can see, as the strength increases, regardless of how you measure this, actually the tensile strength, the ratio will decrease. Okay, so that's something you have to keep in mind. I mean, for both values. So depending, again, as we said, since the crushed coarse aggregate seems to improve the tensile strength more than it does compressive strength, the ratio of the tensile to compressive strength also depends on the type of aggregate. Okay, so in addition to age, the type of aggregates also impact this ratio. So it has been found that compared also to moist curing, air curing reduces the tensile strength more than it does compressive strength. So probably because of the effect of drying, shrinkage cracks in this case. So the ratio of the tensile to compressive strength is lower for air cured than it is for moist cured concrete. Okay, so remember that. Also, incomplete consolidation and air entrainment will affect the compressive strength more than they do the tensile strength. They will affect tensile strength, but their impact on the compressive strength is higher. Okay, so in general, though, the ratio of the direct tensile strength to compressive strength ranges from about 0.07 to 0.11. Since the split in cylinder value tend to be slightly higher than the direct tension values, So the ratio of the split in cylinder tension value to the compressive strength ratios are slightly higher, from about 0.08 to 0.14. For flexural tests, usually they give results that are substantially higher than the direct tension tests. So the ratio of the flexural strength, or the modulus of rupture, to compressive strength ranges from about 0.11 to 0.23. Okay, so that's actually, I mentioned about the which higher and which lower in the previous slide. Okay, and how we determine the tensile strength. Okay, so a number of expressions have been developed to represent basically the relationship between flexural and compressive strength. The relationships are, given by ACI, as you can see here, equation number 4. Okay, so this is the modulus of rupture basically for SI units, and this is for inch-pound units. 0.6 times square root of F prime C, and in this case 7.5 times square root of F prime C. Okay. Also, an analysis of a wide range of data, however, indicates that the best fit expressions for both split-in tension and flexural strength of concrete depends on a power of the F prime C that is greater than the square root. Okay, as you can see in equation 5. This is for the split-in cylinder test. Okay, so this is the SI units in MPa. This is in inch-pound units. As you can see, the power here is 0.55. It's higher than the square root. Okay, and the modulus of rupture, basically the power is 2/3. Okay. So that's, like I said, based on an analysis of a wider range of data. That's where the expression was basically developed. Okay. So the relationships, in these equations above, along with several others, are the ones actually used to develop these curves, as you can see here. Okay. Okay, so as shown, the figures, the actual relationships between the tensile and compressive strength vary widely, and they exhibit really significant scatter, as you can see. Okay, nonetheless, the relationship, a certain pattern is established. Still, there is a lot of scatter, as you can see, relating the compressive strength to the modulus of rupture or the split-in cylinder test. Okay, just something to keep in mind. Okay, so basically I will stop here for this lecture, and next time we are going to discuss the compressive strength and the factors that will affect the compressive strength. Okay, so until then, thank you for watching, and see you next time.